Welcome back, students. In this video, we're going to cover lesson 11-5. This is cross sections and solids of revolution. Right now, if you're trying video 11.4, I believe I have no sound. I have no idea what happened, but try to put a comment. I'm going to try to see if I can dub the the audio with it later, but for now, follow along with the notes. Excuse me. Apologize, it's late, thirsty. So we're going to try to do the best we can with this. 11-5, cross sections, solids of revolution. We have GR 4.1, GR 4.2. I can identify shapes of 2D cross sections, of 3D figures, and 3D objects made by rotations of 2D figures. All right, so let me try to make sense of this. So a cross-section is an intersection of a solid figure and a plane. So, this gray is the plane. So if you cut this pyramid with this plane, sorry that the paper keeps moving. So because it's a pyramid, you see the square base. So what you would end up with, you guys know I can't draw. But if this passed through, you'd have a triangle on top that would be a square on the bottom and then a square. Or rectangle in this case, because it's a rectangular base. Excuse me. Let me move this closer, and I hope to God I got sound this time. All right, so if we cut it vertically, it's going to be a triangle, or in this case, an isosceles triangle, because these guys will be congruent. And if you cut it diagonally this way, you're going to end up with a trapezoid. If you guys have been in my classroom, you'll know Bucky's the fish tank is a trapezoid, so it kind of looks like that. All right, so a three-dimensional figure has plane symmetry if the figure can be mapped onto itself by reflection. So if we reflected this over here, if you cut this rectangular cube in half, you'd have two square cubes. Cross sections of a right circular cone are called canonic sections are conics. So that'd be this guy. Solids of revolution. That is a three-dimensional figure that has axis symmetry if the figure can be mapped onto itself by a rotation of 0 to 360 on a line. So 0 is obviously going nowhere. 360 is obviously an entire circle. So that's kind of what it's saying. All right, so down here, describe each plane of symmetry. For the rectangular prism. So these dotted lines, it's a three-dimensional figure. So this is the backside. So a rectangular prism. Let me just double check my notes, but hold on. Yeah, that's what I thought. So it says there's three. Now, well, okay. These are planes of symmetry, not axes, so I'm getting my terms confused. So the reason there's three. All right, so if you cut it in half like this, you're going to have two squares like we did over here. So there's one. This is diagonal. Not going to work. This is cut vertically, but this way. So if you could fold it onto itself. So yes. This horizontally again. Not going to work. But this over here vertically the other way. So there's your three. All right, example one, check. Describe each plane of symmetry for the regular polygonal prism. We're going to do that in the process here. So part A. How many planes of symmetry does it have? So you have one across because you can cut it into two equal halves. And then you have one for every edge here. So, or it's every vertice because every edge would be where an angle and a side meet. So you have 1, 2, 3, 4, 5, 6. So how many? 6 total. So again, let's just do 1, 2, 3, 4, 5, 6. Okay. And then use the correct term. All right, so it has one that is blank to the base. That is parallel to the base, and that's this guy. All right, and it's to the center because it's right through the middle. All right, and then it also has 5 that are perpendicular because they go here and they make 90-degree angles. This guy, this guy, this guy, this guy, this guy. So what they say? They said 5. They're perpendicular because they make a right triangle with the ground. And the planes of symmetry pass through so bases would be here, but it passes through the faces. The face is what you see. One vertice through the midpoint of the opposite vertex. So here. So from here to here. Flip over. All right, example 2. We skipped this in class. I'm going to try to do this. I kind of had a hard time, and I'm thinking it was just me, but I'm going to double check. So, example 2, identify the shape of the cross-section of a right cone. All right, so we have a right cone. So let's just draw. Actually won't be over here. So this is a right cone. All right, the intersection of the cone and the plane parallel to the base. So if we were to go through here, all right, so hopefully you guys know I can't draw well, and I apologize for that. But, so the base of this is a circle. If you cut it with a plane, it's going to be a circle. All right, so the intersection of the cone and the plane perpendicular to the base. So if we cut it, let's do this. So I'm going to put this over here. So if we, So if we cut this cone that way, we're going to end up with a right triangle. And so keep this in mind. They use these on the EOC. They love to ask what kind of shape are you going to get once you cut something. All right, so intersection of the cone and the plane with the same slope as the slant height. So if it went that way, so... And it's hard to tell here, so I'm just going to give you the answer. It's a parabola, and that's probably the one and only time you guys will hear me say that this semester. And then the last one, intersection of the cone and the plane with the slope different than the slant height. So this way, and do I have any more? I have a darker blue, so we'll just do... And again, this is really tough to tell. I've never asked these questions before. But this makes an eclipse. So we got a parabola one way and an eclipse the other. I think that's a parabola. They haven't let me out of geometry yet. Every year I'm back here, so I'm not sure. So example 2 check. They want the shape of the cross section. So when it cuts here, what kind of shape is this? And then when it cuts here, what kind of shape is that? All right, so example 3. Identify the shape formed by rotating the two-dimensional shape along the line. So it's too big, but this is a square or a rectangle. So I'm just going to take and roll up a piece of paper because it's the same shape. Whether it's a square or rectangle, when you roll that up, you get the same shape. So can we see? Yeah. I can see all the way down because this is a cylinder. And I showed you guys this in class, and this is definitely on the EOC. Please Please get that one right. Now this guy, so if you twisted it around, so instead of being a square, it's an angle. So you're going to have an angle at the top. So what this is going to make is a cone. Sorry, that was the check. My apologies, but hopefully you guys got that and it will help you. All right, so let's do the bottom over here. So both of these are going to be axis symmetry. And what that means is, if you put a dotted line down the middle, would it map onto itself? I'm just going to do a couple of these. All right, so these two, they definitely could flip onto each other, so that's a check. Notice this guy's like a snake. It has this over here. That doesn't match, so no. Capitol building is perfectly symmetrical. That's a yes. A donut, that's a big fat yes. And a Homer Simpson says, donut. Sorry, that wasn't my best one, but it's okay. The duck, it's a rubber ducky, so technically I would think so, but we're going to say no. So you got these. Over here, looks to me like the bulb, the drum, and the hourglass. The tree may have limbs on one side that are longer than the other, but that's only for you guys that are listening. If you have any questions, please let me know. Send me a message in Focus. That goes for you guys in Miss Brailsford or any other class. If you're in my class, you can also use Teams. And I am in I-103, so if you guys need me, please come see me. I'm there after school every day too. Please consider subscribing, especially if you're not one of my students, because you'll get the alerts when I put these videos out. I will be doing these during the EOC review, so it could be useful. Until next time, have a good night.